Welcome to the last fall session of the New York Combinatorics seminar. Our speaker today is Max Hlavacek, and they will be talking about subdivisions of shellable complexes.
Thank you so much for the introduction. So my name is Max. I am a PhD student at UC Berkeley, and today I'm going to be talking about a project that I have been working on with my collaborator Liam Solis, who is in Sweden right now. So the plan for today is that first we are just going to give some context about what people are doing in the field of computing these specific enumerative polynomials concerning simplicial complexes. And we're also going to give some background info so that at first we can all understand what all the words are in the main question of this talk, which is the h-polynomial of the barycentric subdivision of the boundary complex of a cubical polytope real-rooted. So we're going to say, okay, what is an h-polynomial? What's the barycentric subdivision? What is the boundary complex of a cubical polytope? And we're also going to give some context about like what work people have been doing in asking questions about these enumerative polynomials. So then we're going to outline kind of a technique that Liam and I use to think about this problem, which combines kind of two ideas, the idea of a shellable complex and the idea of polynomials with interlacing roots. So together we're going to talk about how these two concepts can make a method for us to think about questions like this. And then finally, we're going to talk about what other situations can these methods be applied to. And throughout, feel free to jump in, ask any questions in the chat, and I'll try to keep an eye on it. I also realized that when I have full screen, I can't quite see the time, so I might ask you, Sandra, a few times to see what the time is. Okay, so first, what is a polytope? So one definition of a polytope is the convex hull of a finite set of points in Euclidean space. So what we do is we pick a bunch of points in space and then we saran wrap them, and the resulting object is called a polytope. So in this talk, we're going to be talking about the face structure of a polytope a little bit. So what the face of a polytope is like if you take a hyperplane and you kind of lay it against the polytope, it's the parts of the polytope that you can get by laying a hyperplane along the polytope. So for example, with this three-dimensional polytope here, can everyone see my cursor? Perfect. We have several different types of faces. So first of all, we have these two-dimensional faces, these triangles. Depending on the polytope, they're not always triangles. They can be any other shape. We have these one-dimensional faces, which we call edges. We also have the zero-dimensional faces, which are the vertices of the polytope. And finally, we have the empty set as a face of the polytope. So then what we often do is we think about the whole set of faces of a polytope as a complex. So the boundary complex of a polytope is the set of faces, not including the polytope itself, because we usually consider the whole thing as a face of itself. So for example, with this two-dimensional polytope, the whole polytope would include the like the two-dimensional 1, 2, 3, 4, 5, 6, 7 heptagon. But the boundary complex is just the collection of these edges and vertices. For the three-dimensional example here, this whole shape would be the polytope itself, and the boundary complex is the collection of these triangles, edges, and vertices. So one specific type of polytope that we are going to be talking about in this talk is a simplex. And a simplex is the convex whole of n plus 1 points in Rn. So if we're in 2 dimensions, we can take 3 points. And if we take the convex whole of that, we have a triangle. Oh, again, I forgot to write this, but we're assuming that they're like not on any specific hyperplane. They're kind of generally distributed. If you are in 3 dimensions and you take 4 points and you saran wrap them, you would get a tetrahedron. And then I tried to draw a 4-dimensional simplex, but I couldn't really do it. So one kind of interesting thing about a simplex is any subset of the vertices forms a face. So for example, if we take this tetrahedra, we have 4 vertices. If you pick any subset of those 4 vertices, and then take the convex whole of that subset, you get a face of the tetrahedra. So if I take these 3, I get this triangle. If I take these 2, I get this edge, and so on. So this is not the case in general for polytopes. So this brings us to our discussion of simplicial complexes. So a simplicial complex is a family of sets that is closed under taking subsets. So for example, let's say we start with the sets 1, 2, 3, and 3, 4. So if we are going to complete this set of sets so that we actually have a simplicial complex, we need to include a few more sets. So what sets do we need to include? Well, since we have 1, 2, 3, we need to include all the subsets of 1, 2, 3. So 1, 2, 2, 3, 1, 3, 1, 2, 3, and also all the subsets of 3, 4. We already have 3, then we need to add 4, and then finally we also have the empty set. So this is kind of the abstract definition of a simplicial complex. And in general, if you just take a bunch of sets, you can't always come up with like a geometric picture in Euclidean space that represents like kind of a geometric realization of your complex of sets. However, for a simplicial complex, you can always draw a collection of simplices that kind of geometrically represent your abstract simplicial complex here. So for this example, we're drawing a picture so that we have a bunch of simplices, and every subset in our list of sets corresponds to, if we take the convex whole of each set, corresponds to a face of this picture. So for example, we start with 1, 2, 3. Then we have all of the subsets of 1, 2, 3. And since this is a triangle and thus a simplex, all of the subsets are faces of this triangle. Then we also have 3, 4, and then the vertex 4. So this is kind of a geometric realization of this simplicial complex. So now we are ready to talk about like what are some enumerative questions that people in discrete geometry and geometric combinatorics ask about simplicial complexes. So I think one thing that when I see any kind of polytopal complex, I ask, okay, like how many faces of each dimension do we have here? So here we can count the number of vertices, the number of edges, and the number of filled-in triangles. And so that is called, we can encode all of these in the coefficients of a polynomial, and that is called the f-polynomial. So for this subdivided square right here, this is a simplicial complex, and we're going to be seeing simplicial complexes that look a lot like this when we start talking about barycentric subdivisions. So here, we always say that the constant term is 1, and then the coefficient to x is going to be the number of vertices. So there's 9 of those. The coefficient of x squared is going to be the number of edges, and I believe previous me counted that there were 16 of these. And the coefficient to x cubed is the number of filled-in triangles, and there's 8 of those. So this is the F polynomial of the simplicial complex. So there are a lot of nice results concerning F polynomials, like people ask like, what kind of shape do the coefficients make? And in particular for simplicial spheres, people have something called the Dean-Somerville relations that make it so that like if you know half of the coefficients of the F polynomial, there is like this summation formula that gives you the other half of the coefficients. And so questions like that bring us to the H polynomial. So the H polynomial encodes exactly the same information as the F polynomial. However, what we do is we just do a basis change to the F polynomial. And the reason why this polynomial is interesting after this basis change is, for example, the H polynomial often satisfies stronger properties than the F polynomial in the specific properties that I like to study, which we'll get to on the next slide, which include like unimodality, real-rootedness. And another reason why people like the H polynomial is that the Dean-Somerville equations that I just mentioned that have this kind of like complicated formula relating to coefficients of the F polynomial for simplicial spheres. In the H polynomial world, these relations, all they say is that the H polynomial is symmetric. So some like important theorems and relations are very nicely formulated in the H polynomial world when they're a little bit more messily formulated in the F polynomial world. And lastly, the H polynomial has a lot of relations to kind of the shellings of simplicial complexes, and we'll talk a little bit about that later. Okay, so we have covered most of the like definitions of the first part of this talk. Does anyone have any questions? And Sandra, how am I doing on time?
It's 12:15.
It's 12:15.
Yeah.
Perfect. All right. Okay. So now I'm going to be talking about some questions that people ask about these H polynomials that we included on the last slide. Oh, actually, I realized I forgot to say, for this specific simplicial complex, the H polynomial of this is 1 plus 6x plus x squared. And some of you who might do like the sense statistic stuff might recognize that I think that this H polynomial here, we'll see this later, but is like some specific type of like type B Eulerian polynomial. So we will get into that more deeply later in the talk. Okay, so when I see a polynomial with positive coefficients, there are a few properties that I like to ask. So some properties that people who study kind of the enumerative sides of the simplicial complex ask is, what simplicial complexes have H polynomials that satisfy unimodality? And what that means is that the coefficients go up to some point and then they go down. So once you go down, they can't come back up. And then the stronger property that implies unimodality is real-rootedness. And as the name suggests, this just means that the polynomial has real roots. So a lot of times, maybe people are trying to ask like, oh, like, is this polynomial unimodal? I don't know how to prove that. Maybe I can prove that it has a stronger property because there are a lot of techniques for proving that polynomials have real roots. So I think kind of the foundational result in discrete geometry that has to do with the H polynomials of simplicial complexes is this G theorem by Balera, Lee, and Stanley. And so what I have on this slide is a consequence of the G theorem that is stated in the words used on the top half of this slide. So first, I realized I have not defined a simplicial polytope. So a simplicial polytope is just a polytope in which all of the faces are simplices. So what this theorem implies is that the boundary complex of a simplicial polytope, so that's a simplicial complex. And if you take the h-polynomial of that simplicial complex, it will always be unimodal. And so since then, people have been expanding and exploring this statement in all sorts of directions. And one of the directions that people have gone is like, are there certain simplicial complexes that satisfy stronger properties than just being unimodal? So in 2008, Brenti and Welker published this paper that says if you take a simplicial complex and all you know about the simplicial complex is that the h-polynomial has positive coefficients. So that's not always true, but it's a pretty common property of simplicial complexes. Then if you do this operation on the simplicial complex called taking the barycentric subdivision, we'll define this soon, then you will get a new simplicial complex, and this new simplicial complex satisfies a much stronger property of the h-polynomial having actually a real-rooted h-polynomial. So then they asked this question, like, is it true that if you just take a polytope and you take its boundary complex, so this polytope doesn't even have to be simplicial, if you take the barycentric subdivision of this, and taking the barycentric subdivision always results in a simplicial complex, and then take the h-polynomial of that, will you always get a real-rooted h-polynomial? So this is a pretty hard question because, you know, polytopes there's a lot of them. So one place to start is, so they already did the case as a special case of their theorem for starting with a simplicial polytope. So one place to start is by starting with a cubical polytope and taking the barycentric subdivision of the boundary complex of that, and then seeing, okay, does that h-polynomial have real roots? So this is kind of like a first step towards the more general question about boundary complexes of polytopes in general. And a cubical polytope is a polytope in which all the faces are combinatorially equivalent to cubes. So for example, if we look at this little polytope here, each of the faces has 4 sides and 4 vertices, so it's combinatorially equivalent to a square. Does anyone have any questions about kind of the main question that we're going to talk about in this talk?
A quick question. What is barycentric subdivision?
Good question. So the barycentric subdivision, so there is kind of a definition of barycentric subdivision involving the face lattice. So it's kind of like we're making a simplex out of each chain in the face lattice of your polytope. So in practice, how we actually do this is, for example, if we start with this square, which is what we're going to be using a lot in this talk because we're doing cubical things, what you do is you put a vertex inside every face. So we're kind of labeling each face with a specific vertex. So we put a vertex inside of it because that represents kind of the 2-dimensional face. Then we put a vertex on each edge. And then we also put a vertex for each vertex, but those are already vertices, so we don't really have to do anything there. And then we take, then we kind of connect everything up, take convex holes where it makes sense, and we get this barycentric subdivision. Basically, we take a convex hole between these new vertices if they form a chain on the face lattice of the original polytope. Does that answer your question? Perfect.
I was just going to add that the root word for bary is weight, right? So you're basically kind of finding the centers of the weight centers of each face, kind of.
Oh, that's a good way of thinking about it. I did not know what bary meant, so thank you. Okay. So we have kind of one question to start off with, which is we start with a cubical polytope. If we take the barycentric subdivision of the boundary complex of this, so we basically turn all of the cubes on the faces into this, and then take the h-polynomial, is it real-rooted? So we're going to split kind of this question into a process and talk about kind of each step coming up. So the first step is we are going to use the idea of a shelling, which we will define on the next slide, to decompose our subdivision into disjoint pieces. So it's going to be split up into little bite-sized pieces, specifically so that those pieces do not overlap at all, not even like on an edge or not even at a vertex. Next, we are going to find all possible h-polynomials of these bite-sized pieces. So since specifically we're thinking about like a specific subdivision of a specific type of polytope, we can do that in this case. And then lastly, we are going to use the idea of interlacing polynomials to show that the h-polynomial of the whole subdivision is real-rooted. And I guess I want to talk a little bit more about like how do we get from the bite-sized pieces to the whole complex? Well, it turns out that since we are breaking up our subdivision into disjoint pieces, if you have a bunch of disjoint pieces and you take the h-polynomial of the pieces and then you want to find the h-polynomial of the whole thing, you just add them all together. And in general, if you have a bunch of real-rooted polynomials and you add them together, you don't get a real-rooted polynomial. But the theory of interlacing polynomials can be used to tell you like, oh, when does that actually happen nicely? Okay, so the first question here is, what is a shelling? So we start with a polytope and we're looking at its boundary complex. So we have a bunch of faces. And we are going to look at the highest dimensional faces here. So for this specific picture, I think we have 10 facets, which is the word for highest dimensional faces. So we have 10 of these squares. And what a shelling is just an ordering of those squares that satisfies some of these like recursive properties here. So first of all, that the boundary complex of like the first face you choose is shellable, and then if you take the intersection of the face you just added with all the previous faces, then that's the beginning of a shelling. So there's like this recursive definition here. What I kind of think about it is like you have to go from one, like the next one has to be touching the first one, and like you have to have these like kind of nice connectivity properties of both of like what you're already including and what you have yet to include. So let's see an example of a shelling. So first, we just have to pick one because if we're doing an order, we have to start somewhere. And next, if we're doing a shelling, we could choose any of these 4 faces that are touching our first face. So in this example, we're going to choose the back face. This one, 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 this one. So that is an example of a specific ordering of the facets here that would give you a shelling. Okay, so now we've been talking a lot about complexes and simplicial complexes. And so I'm going to define a relative complex. So I guess the relative complex is that you take some kind of polytopal complex, so like a polytope and all of its faces, and then you remove a different complex. So a relative complex is not like a complex in of itself, because a complex is like a collection of polytopes that satisfies some like specific properties, but we can still talk about it. We can still compute things with it. And so we're going to use our shelling to construct some specific relative complexes. And so I guess here's the specific notation for what we're going to do, but let's just actually look at a picture. So I guess with this picture here, imagine that all of the faces of this thing are already subdivided barycentrically. I just didn't want to draw them on the big picture because then there would be way too many lines. So so we're going to start with the top face, and the next thing that we did in the shelling order that we previously established was going on to this back face. So you may notice that when I draw this picture representing the back face, something is missing. So we're missing this top edge. Does anyone know like why we might be missing that top edge? So since we are trying to make a disjoint, we're trying to chop up this big shape into disjoint pieces, we're going to use the shelling order to do that. So we already have this, we've already counted this edge in the top face. So we don't want to count that edge again. So we're going to remove it from the next face we put. And so we're really just using this order to determine which edges belong to which faces. So basically the edges belong to the face if it was put there first. Okay, so let's keep going. Next, we put in the side face here, and we remove two of the edges and also the vertex that's there as well, and these two vertices, because they're already included by the faces that we've already filled in. So we keep going. Again, this one has two faces missing. This one has three missing. And we go all the way around. And then finally, when we put that last face in, since all of its edges and vertices have already been filled in using the previous faces in the shelling order, we just only have the interior. We remove everything on the exterior. Does anyone have any questions about this construction here?
No, that's good. Thank you.
Okay. So now, as I mentioned before, if I want to compute the h-polynomial of this thing, if you imagine that all of the facets are subdivided, all we have to do is take the h-polynomials of these things and add them together, and then we'll get the h-polynomial of the whole thing. So one thing we can do is we can show that the h-polynomials of each of these individual things are real-rooted. And that's not enough to show that the sum is also real-rooted. So we need to talk a little bit about interlacing polynomials. Okay, so what does it mean for two polynomials to be interlacing? So if we have a polynomial p and a polynomial q, and these are both real-rooted polynomials, their interlacing is if these are like the zeros of p, these are the zeros of q, they alternate back and forth if you write them out in increasing order. And so this notation right here is just like if there's like kind of this determinant here that you compute to see when you're writing it, if we put p first or q first. So if p and q are interlacing, we can either write p is interlacing less than q or q is interlacing less than p, and we just have this determinant to figure out which one goes first. So again, in 2008, Borsia and Brandon proved that if we have a sequence of interlacing polynomials, then if you take any non-negative combination of those polynomials, you get a real-rooted polynomial. So in particular, if I have a bunch of polynomials, I show that they form an interlacing sequence, then if I add them together, which is what we are trying to do on the previous slide, then the big sum polynomial is also real-rooted. And Sandra, can I check in on the time?
Yes, it's 12:32.
Oh, it's 12:32.
Yeah.
Okay. So this kind of brings us to this kind of framework theorem that Liam and I have. So what this is saying is that if I have a shellable polytopal complex with a specific shelling, and I also take the subdivision of each of the faces, some specific type of subdivision, if the h-polynomials of kind of the bite-sized pieces I constructed from the shelling form an interlacing sequence, then the h-polynomial of the whole subdivided thing is also real-rooted. So this is a very vague statement. I haven't told you what the polytopal complex is. I haven't told you what the subdivision is, but this is just saying if this works out, then we're all good. And so kind of what we want to do is see if we can apply this general method to the specific case of the barycentric subdivision of cubical polytopes. So here is a picture. If we had a 4-dimensional cubical polytope, then the faces would look like these cubes, and then specifically the relative complexes of induced by the shelling would look like these cubes with some amount of facets removed. So what Liam and I did is we took the barycentric subdivision of each of these pictures here. And also it's hard to see in these pictures, but we are actually, the cube inside is included. I just didn't shade it in because I was shading in which facets are included. So I took the barycentric subdivision of all of these. And when we computed them, we got an interlacing sequence for all of the h-polynomials of these except for this tabletop thing. So we were like, okay, maybe we want to find shellings that don't make it so that we have a tabletop type thing as part of the relative complex induced by the shelling. So we came up with a definition of a specific type of shelling called a stable shelling. And so in general, this property can apply to any polytope, not just cubical ones. And there is kind of a complicated that takes time to parse definition that uses the face lattice of your polytope. But for cubical complexes, it's kind of easy to see what the definition is. So if I am looking at a shelling of a cubical complex and I want to know, is the shelling stable? I look at all of these like relative complexes that come out of the shelling. And what I do is I look at the facets of those, or I look at the faces of those facets that are included and which ones are not. So it turns out that the shelling is stable if all of the relative complexes satisfy the properties such that you can't have an opposite pair present in the faces that are included and an opposite pair included in the faces that are excluded. So let's look here. So for example, with this cube here, we do have an opposite pair in the faces that are shaded pink, but we don't have any opposite pairs in the unshaded faces. The thing that makes this tabletop bad is that we have an opposite pink pair and an opposite white pair. Okay, so now I think I'm going back into my examples being 2-dimensional because it's easier for me to draw that. This is kind of where these polynomials called type B J Eulerian polynomials come up in our work, because what we really want to do is to compute all of the polynomials of these bite-sized pieces to see if they form an interlacing sequence. So the type B J Eulerian polynomials, where do they come up in math? So they do have an interpretation in terms of the sense of sign permutations. Since I am a discrete geometer, I usually, when I see a special family of polynomials, I usually think of the interpretation in terms of like some polynomial coming from some specific polytope. So when I think of the type B J Eulerian polynomials, I think of the -1, 1 cube with a bunch of facets removed, and then look at the h-star polynomial of that. So the h-star polynomial is a specific polynomial that pops up in Earhart theory. It's kind of similar in flavor to the h-polynomial, but the definition is different. But yeah, so no worries if you don't know what that is, but this is just kind of how I think of the type BJ Eulerian polynomial. So it turns out that if you have a d-dimensional cube, you take the barycentric subdivision of it and you remove j of the faces where j is less than the dimension. So in this specific picture here, the dimension is 2. So I can remove no faces, I can remove one face, or I can remove 2 faces. So this proposition just only applies to these first 3. Then the h-polynomial is exactly the type B J Eulerian polynomial. And how we computed this was using Ehrhart theory, which I'm not getting into in this talk, but is kind of, you count a bunch of lattice points inside of polytopes. So we have not yet computed the h-polynomials of these 2 complexes, or relative complexes. So what you can do here is there's some kind of like reciprocity theorems in h-polynomials and h-star polynomials that we use. And it turns out that using kind of that machinery, you can see that the h-polynomial of these 2 is you take a type B J Eulerian polynomial, you reverse the coefficients, and you multiply it by something. In this case, just x. So putting this all together, it turns out that these type B J Eulerian polynomials, and also the kind of edited versions of them where you switch around the coefficients and multiply by x, form an interlacing sequence. So that means that, I guess I want to kind of go back to here. So since the h-polynomials of these bite-sized pieces form an interlacing sequence, then we can add them together and get a real-rooted h-polynomial of the whole thing. So what this theorem says, that if we have a cubical complex that has a stable shelling, so not just a shelling, but a stable shelling, then the barycentric subdivision has a real-rooted h-polynomial. So unfortunately for us, since we just kind of defined this notion of a stable shelling, it was unclear to us if all cubical polytopes have a stable shelling, or if have a stable shelling. And it's still unclear to me if all cubical polytopes have a stable shelling or not. So what we did is we went into the literature and found some specific families of cubical polytopes and more general cubical complexes that we were able to prove do have a stable shelling. So for example, if you take a bunch of cubes and pile them up, you can prove that that has a stable shelling. That's just kind of like this zigzag ordering. If you take a specific type of cubical polytope called a cuboid, and so what a cuboid is like you start with a cube and then you kind of add these like little belts around it. So this is a picture of a cuboid. We start with a cube, then we put this like belt in this direction, this belt in this direction. You could also put a belt in the third direction here. That the boundary complex of that has a stable shelling. And lastly, a capped cubical polytope, what that is you start with a cube and then you start replacing the faces of that with like little kind of cubes with one face removed. So for example, this is like we're taking 2 cubes, we're removing the face of one of them and then gluing them together. So if you keep doing that in more and more complicated ways, you get the family of cubical polytopes called capped cubical polytopes. So all of these cubical complexes have stable shellings, and thus the h-polynomial of all of these cubical complexes pictured here is real-rooted. So that's as far as we have gotten in that direction with the cubical polytopes. So I want to kind of revisit this game plan. So before, when we saw this slide, this said, does the barycentric subdivision of boundary complex of cubical polytopes have real-rooted h-polynomials? So if you kind of go back to our most general theorem that's just starting with a complex and a subdivision, we can just replace these things with with a different type of subdivision or a different type of complex. And we can still use the same game plan. Maybe it might not work, but we can at least attempt. So we can use the idea of shelling to decompose our complex into disjoint pieces. We can find all the h-polynomials of these bite-sized pieces. And if we're lucky, then these h-polynomials form an interlacing sequence, and then the h-polynomial of the whole complex is real-rooted. So we tried putting a few other collections of words into these blanks. And we were able to have a few other positive results here. So the technique outlined on the previous slide also works if you take barycentric subdivisions and then simplicial complexes with h-polynomial having positive coefficients. So again, this is exactly what Brenti and Welker proved in 2008, this first bullet point, but this is a different methodology than what they did. So we just wanted to see if our methodology could recover their results. And then there is a different kind of combinatorial subdivision called an edgewise subdivision, where you just kind of subdivide things by taking a bunch of like lines parallel to the edges and chop things up in that way. And so the edgewise subdivisions of simplicial complexes and certain cubical complexes, the ones that admit a stable shelling, this method also works for. So after we put out this paper, later Christos Athanasiadis proved that all cubical polytopes have a barycentric subdivision with a real-rooted h-polynomial. So his methods were different. So what he did is there is a specific type of h-polynomial. So the h-polynomial that I defined to you is only defined for simplicial complexes. So some people have defined a specific h-polynomial for cubical complexes, and he was able to use that h-polynomial to prove this result for all cubical polytopes. So I'm still curious, like if all cubical polytopes do have a stable shelling, and if so, then we can also use our technique. My future work also includes the questions, are there other families of polytopes, not necessarily cubical or simplicial, that admit stable shellings? And from those stable shellings, can we get some real-rootedness results? And then the other question is, do all polytopes admit a stable shelling? So again, I don't have a counterexample to this, I don't know. And in particular, it is true that all polytopes, their boundary complexes, admit a shelling, and this shelling is called a line shelling. So kind of the person who proved that all polytopes admit a shelling did a construction based on like shining lights on the polytopes. So if you shine an imaginary light on the polytope, you construct an order based on like which faces the light hits, and that is actually called a line shelling. So Liam and I tried to construct a line shelling that is guaranteed to also be a stable shelling, and we are still unclear whether that exists for all polytopes or not. So that's also in our future work. So thank you so much for your attention, and yeah, let me know if you have any questions.
Thank you. That was very good. We'll thank the speaker, and I'll turn off the recordings and we'll take questions.